Go.
Hi, everybody. Welcome to our presentation on earthquake detection. My name is Nidhi.
My name is Luna.
The motivation for our project was that traditional methods of earthquake detection are limited in their accuracy and efficiency, which is why development of a CNN for earthquake detection can help improve the quality of earthquake monitoring systems worldwide.
Our goals is to detect earthquakes with convolutional neural networks, augment seismic data, process data with OBS-PI, which is a library to process seismic data, and create a demo dataset.
The progress we've made so far includes creating new CNN layers, implementing our base model and QuakeNet model, loading and pre-processing data, transforming the data, and working on visualization methods. The tools we used were OBS-PI, which, as Luna mentioned, is specifically used for processing seismic data. We also used TensorFlow, Pandas, and NumPy. We focused on two different models commonly used for seismic data. First one is ConvNet Quake, which is a CNN model that uses a series of 2D convolutional layers, followed by a fully connected layer to classify whether the given input waveform corresponds to an earthquake or not. Similarly, UNet also takes the earthquake data. Specifically, it is used to locate the earthquake epicenter by segmenting the waveform image and identifying the region's highest seismic activity. And here's the structure of both of the layers. On the left, we have UNet structure. On the right, we have ConvNet Quake.
We use the Adam optimizer which calculates an adaptive learning rate for each parameter based on the estimates of the first and second moments of the gradients. The loss function we use is called the cross entropy loss, which is commonly used in binary classification problems. Our model is predicting whether a given seismic signal contains an earthquake event or not, and the labels are binary, 0 for no earthquake and 1 for earthquake. Our loss encourages the model to predict high probabilities for positive samples, earthquake events, and low probabilities for negative samples, which mean no earthquake events.
Great. So the way we pre-processed our data, so the data set consisted of different seismic activities, such as the start and end time, latitude, longitude, depth. And then we had a data writer method that wrote TF record files or TensorFlow record files to a disk. And it essentially converts the seismic waveform data into a binary format that can be loaded during training. We'll talk more about that binary format later. And then we had a data reader, which reads the TF record files, and it also can convert the binary back to seismic waveform data. Then we have data pipeline, which created a queue operation to stream the data for training. And then it also utilizes the data reader functionalities. And finally, we had the data input-output file, which Luna will talk more about the different ways we loaded the data and wrote it.
A stream object is a container for multiple trace objects that share attributes such as station location, network code, channel code, and start and end times. Here's an example of the output from reading stream data. A catalog is a list of known seismic events. It contains details about the time, location, and magnitude for each seismic event. And here is an output of how we read the catalog from the CSV files, where each row represents a known seismic event. Here is what the CSV file looks like for a catalog.
And we really wanted to have easy methods that can help convert from OBS-PI stream object to a NumPy array, and that's exactly what the stream to array method does. We also had a method that converted from the NumPy array back to the OBS stream object. Our pre-processing also included normalization of data and creating of sliding windows. Like I mentioned earlier, the pre-processed data was stored in the TF record files, which was later on used in training. And speaking of the binary format that I mentioned earlier, the TensorFlow records consist of two categories, negative and positive. Positive refers to the earthquake signals where it was an actual earthquake, and negative refers to non-earthquake signals. The positive example consists of a length of 3,000 samples per channel, and each file corresponds to a single earthquake event, and the data set includes earthquakes of different magnitudes and distances. Negative examples were randomly sampled signals from continuous seismic data, and they had the same length and number of channels as the positive examples. And this was very useful to help train our model to detect the difference between an earthquake and non-earthquake signal.
But we can use both catalogs and TF records to train our convolutional neural network model. We have implemented 5 visualizations, which can be shown on the slide. We will be generating results once we train and test our data set.
And here we found this in a repository that's similar to our project, and we kind of wanted our visualization results to look like this. On the left, or on the x-axis, we have time, and on the y-axis, we have magnitude. The subgraph on top is representing the S wave, or the secondary wave, which is slower. And then on the bottom, we have the P wave, or the primary wave, which is a lot faster and occurs before the S wave occurs. And we just want to achieve that clean format. So the next steps include fine-tuning our model, training and testing our data set on our model, and generating visualizations of the output. And here are our references. Thank you.